Hello students, today we are going to discuss the topic of potential due to different charged bodies, because last class we completed the potential concept and potential energy concept, and electric field and potential relation concept is over. Now we are going to discuss potential due to the charged bodies, different charged bodies, what is the potential equations we are going to derive. In this case, first if we come across a case of, we are taking the first body, conducting charge sphere we are taking, in that first halo sphere. Next we'll go for solid sphere. Then after we'll go for non-conducting charge sphere we are going to take. In that also we are going to discuss about halo, non-conducting solid halo sphere, and uh, conducting, non-conducting, halo, solid sphere we are going to discuss. So these are the two topics we are going to discuss now. That means four conditions we are going to discuss now. Now we'll discuss the conducting charge sphere potential due to that charge sphere we are going to discuss. First one is halo sphere. Consider one of the halo sphere. This is one of the halo sphere. You take it, which is charged 1. If the charges are given to this, then the charges will be accumulated on the surface of the sphere. You know that. So here we are taking the charges on the surface of the sphere. Now this sphere having radius r, that sphere radius I am taking from here. This is the radius r. Now we choose a line, that means from the charged body, from the center to outside here. I am choosing one of the line here. This is the one of the line I chosen here. On this line, I am taking some points here. So first point is I am taking at the center. That point I am calling as A point. At the center I am calling as A point. And on the surface I am taking another point, that is B point. And outside of this one, at a point of distance, I am taking that point as C point. Now this is one of the halo sphere. So now we are calculating potential due to this halo sphere. Concept of this potential due to halo sphere, to explain this one, already we discussed in the definition. Okay, whenever you taken any test charge at infinite, and whenever you bring this test charge from infinite to any point, how much work you are doing, that work will be stored in the form of potential at that point, we can say. So here also we are going to discuss the potential at C point, B point, A point. From outside to inside we are going to calculate now. So in this case, capital R is the radius of that sphere, if you say, and small r is the distance of the points, I can say here. So first case, that is case 1. Case 1, in this case, the distance of the point is greater than radius. That means outside of the radius of the sphere, that is at C point. That means if the charge is taken, that means if the point is taken outside of the charge sphere at a point of C, the distance of that one is greater than radius of the sphere. In this case, what is the potential at that point? Potential due to any charge sphere, this total body having charge, that charge is equal to capital Q. If you say due to the charge, the potential at this point is equal to work done to bring the test charge from infinite to that point. So already we discussed, that is nothing but 1 by 4 pi epsilon naught. The charge is Q by distance of that one, that is nothing but R. That is RC, I can write distance of that point, that is RC, because R is greater than capital R. So this is the equation for the potential due to the charged body at point C. Similarly, what is the potential due to at point B point? That means at B point, that means R is equal to small r is equal to capital R. That means distance of the B point is equal to radius of the sphere, because B point is exactly on the circumference of that sphere, halo sphere. So in this case, I can write the same concept, because here also you bring the test charge from infinite to the same onto the surface. The work done is equal to nothing but due to the charge of this one. So that is also, I can write potential at B point is equal to 1 by 4 pi epsilon naught. The charge of that one is equal to Q, but the distance, that means what is the point of that one, that is nothing but equal to R. So this is the potential on the surface of the sphere. Now in this case, to bring the charge from infinite to C point, less work is needed, that's why potential is less. But you do more work up to the B, that's why potential is more. But the potential depends on the distance of that point from the center of the sphere. So the center of the sphere is okay, from the center of the sphere to point B is radius distance. That's why we are taking the radius distance here. Third case, if we come across a case of third one, that means at what point? At A point, that is nothing but I can say distance of RA is equal to nothing but 0. 0 means that is inside, at the center. At the center, RA is equal to 0. So if you apply that concept here, what is the potential? We should not take it as 0 here. That is the most important point to keep in, because here you need to understand you have to do work. Okay, potential always we are calculating based on work done. So here the test charge q naught we are bringing from infinite to the point up to the B, you are doing the work. So how much work you are doing to bring the charge from infinite to the B, the same work has to be done up to the A point also. That means to bring the charge inside also you have to do the work. How much work you have to do, how much work you already done up to the B, the same work you have to do it up to the A point. So that means I can write potential at A point is equal to, if RA is equal to 0 means you should not take it as 0. So that means in this case 1 by 4 pi epsilon naught, that is charge q by distance is nothing but equal to radius of the sphere. It means what is the meaning of this one? The work done to bring the charge from infinite to B point, how much work you're doing, the same value of work done you have to do to bring the charge from infinite to the A point. That means simply the conclusion point we can say, in the case of hollow sphere, the potential at A point is equal to potential at B point, and these 2 point potentials are greater than potential at C point. This is the concept you need to understand. That means potential outside always less and on the surface will be more, inside will be same as surface. So potential at any point. But in the case of electric field concept, already you know that potential, okay, this is the C point, right? So what is electric field? Electric field at center, okay, at C point. Electric field at C point is equal to 1 by 4 pi epsilon naught, that is q by, okay, small r square is the formula. This already been done in the previous classes. So from this point I can conclude one thing. So VC is not equal to 0 and EC is not equal to 0. Now if you can make it as a case of second point, B point, on the surface electric field equation, what is the electric field equation on the surface? That is equal to 1 by 4 pi epsilon naught, that is also q by capital R square you take, because r is the distance of that one, radius nothing but this is. Here also I can conclude the one of the point that VB is not equal to 0 and EB also not equal to 0, both are not equal to 0. But when you come across a case of A point inside there is no charge according to Gauss law or according to concept of the net electric field inside. So what is electric field inside? Electric field at A point is equal to become 0. That means in the hollow sphere, you know that either conducting or non-conducting hollow sphere, whatever it is inside, electric field is always 0. So electric field is 0 means I can say here VA is not equal to 0, but EA is equal to 0. This is most important point you must keep in mind. Electric field is 0, potential is not equal to 0. We'll discuss the graph at a time at the last after completion of the remaining sphere concept also. Now come to the case of second one, solid conducting charge sphere. So in the case of solid conducting charge sphere, consider one of the charge sphere same like previous. This is one of the charge sphere conducting one, which is contains the charge. The charges will be accumulated on the surface, same like the total charge is q, and the radius of this one is equal to same like previous r. Now you choose the 3 points on the surface, that means from center to here, that is the 3 points I can choose it. This is the way you can choose the 3 points. Now these 3 points are located, first point is located at the center of the circle, that is center of the sphere, that is conducting sphere, that is A. Second point is on the surface of the sphere, that is B. Third point is outside, that is at anywhere outside, that is C. Similarly, same like previous, if you observe this outside point, that means the total charge of the sphere is influencing at this point. So if you want to bring the test charge from infinite to the point C, you have to do the work same like halo, because it is not the body either halo or solid, it is only the concept of work done to bring the charge from against the electric field. So previous also charge q, now also charge q, radius is also same, but previous is hollow one, this is now solid one, but you have to do the work to bring the charge from infinite to the same point, previous and this one same. So I can say here first case, that is at point C, at C, that is nothing but RC is greater than capital R. In this case, potential at C point is equal to, we can write, so 1 by 4 pi epsilon I am writing as K, K into charge Q by distance of that point we are taking as RC. So in this case, at this point, I can write electric field also not equal to 0. EC is equal to K into Q by R square. So I can conclude the points here same like previous, that is VC is not equal to 0 at C point, and the electric field at C point is also not equal to 0. This is important to understand here. Next, to go to the next point. What is the next point? The next point is at B point. B point means surface, that is RB is equal to capital R on the surface. When the point is chosen on the surface at that concept, previously solid, hollow one, what we taken solid also will get the same thing, because here the total charge is Q, previous also Q. What is the charge which is accumulated by the previous hollow body and solid body, both are same only. So in this case I can write here, so at this point B, potential at point B is equal to K into, that is Q by capital R, I can write. Similarly, electric field also at that point we can write as B is equal to K into Q by capital R square, I can write. Now in this case, VB is not equal to 0 and electric field at B point is also not equal to 0. This is important point to understand here. Now come to the case of third point, that is what is at A. That means inside the sphere, that is at A point, that is nothing but RA is equal to 0.6. Now here we need to understand, in the case of halo, inside the sphere there is no charges, but this is not the halo sphere, this is the solid sphere. So solid sphere means what happens, it contains many number of charges, not only on the surface, inside also we have a charges. That is important to understand here. This is one of the conducting sphere, so we have a charges inside. But what is the concept here? If the charges are present in the conductor inside, still the net charge will be 0, because electric field is 0 inside. Electric field is 0 inside, because already we discussed conductor. In any conductor, electric field inside the conductor is always 0. So this is a conducting sphere. There is a charges inside, but still what is happening? Electric field inside is 0 here. But potential, here also same thing. If you want to bring the charge from infinite to the inside, how much work you are doing up to the surface, same work you have to do to bring the charge from infinite to inside. So here I can say simply here, potential at A point is equal to not 0, that is K into, that is Q by radius of that sphere, that is equal to capital R here to take. But electric field inside, that is EA, is equal to nothing but always 0. Either it is a hollow one, either it is a solid one, electric field is 0. So that means I can say simply VA is not equal to 0 inside the solid sphere, and electric field is equal to 0, that is EA is equal to 0. These are the points important for the competitive concept questions, so you need to keep it in mind what are the points which are going to be covered. Now we can discuss about non-conducting charge sphere of first one hollow sphere, next one solid sphere. We'll discuss first hollow sphere. This is one of the hollow sphere having charge total is Q on the surface of the charge, having radius R. We taken a line from the center of the sphere to outside. I located 3 points here, A, B, C. The C point is outside of the sphere, A, B is on the surface, A is inside the hollow non-conducting sphere. That is important for us here. First case, what is the case one here at C point? At C point means I can say here RC is greater than radius of the sphere, means the distance of the point is more than the radius of the sphere. In this case, the total charge influence this one, that means you have to do the work to bring the charge Q naught from infinite to this C point. How much work you are doing, that much potential is there at C point. We can write BC is equal to, that is K into Q by distance of that point C. What is the distance of the point C? That is nothing but RC. So already we know that how to take the distance from here to here, that is nothing but RC like here to take. This is important for us, right? Next, in this case, what is electric field? Electric field at this C point is equal to not 0 because we have a charge. So K cube by R square is a small r square is a formula here. Okay, small r square is a formula. RC square is a formula for this. So I can conclude the points here. That is VC is not equal to 0 and EC also not equal to 0. That means at C point, potential is not equal to 0, electric field also not equal to 0. Now go to the point of second case, B point. If you go to the second B point, the B point is that is nothing but at the B point, what is the condition? Distance of the B point is equal to radius of the sphere. The B point is here, the distance of this one from the center is equal to radius of the sphere. So at this point, what is the potential? The potential at B point is equal to due to the charge, means you have to do the work to bring the Q naught from infinite to the B point. So you have to do work, means there is a potential. What is the formula? K into Q by distance of the B point is from the center of the sphere is how much? That is the radius of the sphere. Now this is not 0 here. Now similarly, what is electric field? Electric field already we done in the previous class. Electric field at the center is equal to EC is equal to what I can write? K into Q by capital R square we can write. So I can conclude some points here. VB is not equal to 0 and EB also not equal to 0. This is not C, this is B point. So both are not equal to 0. That is important to understand here. Next, if we go to the point of third case, what is it? Where is the third case? That is at center of the sphere. So this is the one of the halo sphere. So halo sphere means at A point, that is distance of the A is equal to C, center of the sphere, halo sphere. You know that any halo sphere, either conducting or non-conducting charge spheres, electric field always inside is 0. So but here at A point, what the potential means already we discussed. If you want to bring the charge from infinite to the onto the surface, how much work you're doing, same work you have to do to bring it inside also. That means you have to do the work to bring the charge from infinite inside. That means there is a potential exist inside the halo sphere and solid sphere also. So in the case of conducting or non-conducting, potential will be exist always inside. It is not going to become 0. If there is a charge, there is a potential, it never becomes equal to 0, right? So it is going to become 0 only in a particular condition. We'll discuss later. So that means at A point, what I can write here, potential at A point is equal to K into charge Q by distance is equal to radius of the sphere. But what is the electric field at A point? That is always 0 inside the halo sphere, either conducting or non-conducting. So conclusion is potential is not equal to 0, but electric field inside is equal to always 0 in the case of non-conducting sphere. This is one of the important concepts to keep it in mind. Now we are going to discuss one more important last one, that is solid non-conducting sphere we are going to discuss. Now we'll discuss last concept of this charge sphere of spheres, solid non-conducting charge sphere. This is important. One of the cases there we are going to derive the certain relations here. So we here also we taken the one of the charge sphere, that is having charge Q, where the charges are going to be forms on the sphere inside every point of the solid non-conducting sphere. There will be charge present, and I taken a line from the center of the sphere to outside, and I located some points here, that is A, B, C, along with another additional point I taken here, D. So first, if we come across the case of C point, imagine a test charge at infinite. Now you are bringing the test charge from infinite to the point C. How much work you are doing, that much potential is there at this same point. There is no change in the concept what we discussed in the previous. So to bring the charge from infinite to C point is equivalent to previous discussion. Similarly, the potential at B point also similar to previous discussion, and similarly the potential up to the A point also similar discussion. That means in the case of halo sphere or solid sphere, whatever the conducting or non-conducting, potential at C point, B point, A point will be remain same. So I can say here one direct formula based I can write at C point, that is RC is greater than capital R condition. So what is the potential at C point? That is K into that is total charge of the body by distance of that point. The distance of the point is how much here? That is small rc. Now, what is the electric field here? Electric field also similarly, that is we convert as k into q by square of the distance of that point, that is rc square. So already we converted many points like this. Vc is not equal to 0, ec is also not equal to 0. This is important for us to understand. Similarly, go to the second point. That is, what is the second point? Second point is on the surface. On the surface mean at this B point. At B point means the distance of the point is equal to radius of the circle. In this case, I can write here potential at B point is equal to K into Q by radius of the sphere R. This is the one formula, and electric field at B point is equal to nothing but K into same charge Q by, but square of the distance it will be so R square. So here also VB is not equal to 0 and EB also not equal to 0. Electric field and potentials both are not equal to 0. Now come to the case of third point, that is at A point first. Okay, at A point. A point means, what is the meaning of that? RA is equal to 0. Still the distance of the point is 0, but okay, what is the concept here? Potential never be 0, because how much work you are doing to bring the charge from infinite to B point on the surface, same work you have to do to bring the move the charge into, okay, inside the center of the sphere. So here also I can write VA is equal to K into Q by, that is I can write as small, okay, smaller only we have to write, and electric field inside A is equal to always at the center is always 0, because according to the concept of, okay, equal and opposite charges, net charge will be 0, so distance of the point is 0, so electric field always 0 at the center of the either conducting or non-conducting charge sphere. So I can conclude VA is equal not equal to 0 and EA value is equal to 0. Now come to the case of last point. There is a point that is at D point. Now this is the point of our discussion. Okay, first theoretically we will discuss at this point electric field, okay, inside is not equal to 0. Previous class already we discussed electric field at this point is equal to what we discussed. Electric field inside any non-conducting sphere is equal to rho by 3 epsilon naught. R is the formula we derived. So electric field is not 0 means potential also not 0. Anyway, potential is not 0 anyway. But what is the value of potential? So in this case, you need to understand here the potential will be different at different points here. So we can able to calculate the potential at this point, okay, using the concept of electric field at that point, because electric field is changing. So potential also, okay, from center of the sphere to up to the surface, it varies. So the potential, what is the value of potential at the A point, what is the value of potential at the B point, that we have to understand. So here we need to understand, here there is a small correction. At A point potential is not equal to 0 we said, but this formula of potential at A point, that is equal to K cube by R, what we've written is okay, not exactly correct. The potential at A point is equal to, after derivation we'll derive the things, this one, that is in nothing but is equal to, okay, 3 by 2 times of K cube by R. That means potential at A point is always equal to 3 by 2 times of potential at B point. Means inside the sphere potential is more than on the surface, that is 3 by 2 times of potential on the surface. This derivation we can able to do. There is a correction small, this one you have to understand. Potential at A point, that means inside at the center, it is not 0 anyway, correct, but the value of that one is equal to how much compared to surface, that is 3 by 2 times of potential on the surface, because electric field changing from center to surface, so potential also changes. So that concept of how we can say that potential is 3 by 2 times of on the surface, that can be done by calculating the potential at D point. So our discussion is now potential at D point, derivation will do, and we'll understand the potential at A point as well as on the surface also using that formula. Now come to the discussion of the at D point. D point means inside the non-conducting sphere, what is the potential here? Just we discussed before, potential at A point is different, D point is different, on the surface is different, outside is different, because due to non-conducting charge sphere, there exists a charges inside also, there is a change in electric field inside also from center to surface. That's why potential also will be different at different points. So first to understand here, to calculate the D point, so this is the D, which is a distance of R from the center of the sphere. So I taken one charge sphere and this is center, this point is D at a distance of R. Now we are calculating the potential at the D point. So what is the potential at D point? Now this one we are writing compared to the surface of the this one, that is nothing but Vs. S means surface. Now to understand this one, we can go through the relation with electric field, because you know the electric field inside the non-conducting sphere, and using that we can able to solve this one. What are the relations? You know that electric field inside the non-conducting sphere in the previous classes we derived, that is at any point of distance Er is equal to rho by 3 epsilon naught r, because electric field is a vector quantity. Inside, electric field is directly proportional to position of that point in terms of position vector. So electric field at that distance of D point is equal to rho by 3 epsilon naught into r. What is rho here? Rho is called charge density. In this case, this is the total sphere having charge q. It is a solid one, so the charges are distributed throughout the sphere volume wise. So there is a volume charge density here. The volume charge density is equal to total charge by volume of that one, that is 4 by 3 pi into r cube is the formula for this. Now you know the relation between potential and electric field. Using that I can able to find the potential at D point. So what is the relation between electric field and potential? E is equal to minus dV by dr is the formula for that. Already we derived in the previous. Now using this I want dV relation, so I can write here dV is equal to minus E into dr. So this change in potential we are calculating inside, so that means electric field also we required inside here. So variation of potential inside we are calculating from center to any point like this, so we are going to integrate this one. So this is the expression most important to understand. So integral dV, change in potential inside, is equal to integral of change in electric field inside with respect to small change in position, that is dr. Minus is the already according to the concept of electric field always in the direction of decrease in potential concept we need to apply. So here what is the limits of this integration? So here integration means what is the potential? Potential is nothing but work done to bring the charge from infinite to the point. So here I can bring the charge from infinite. So here we are taking the charge q naught. This q naught we are bringing from infinite to the surface. Already you know the formula for bring the charge from infinite to the surface. So using that concept I can able to calculate inside also. So here already you know the potential on the surface. Formula in the previous case we discussed. So I can calculate the limits from surface to the inside up to the D point. So this is the limit we are doing from Vs to Vd. So this is the limit I am applying, because you know the formula for Vs and we need to calculate for Vd is equal to minus indicates the sign convention, that is minus, that is integral. What is E electric field? Electric field formula already we discussed. This is okay, rho by 3 epsilon naught r, nothing but I can write as okay 1 by 4 pi epsilon naught into, that is nothing but what I can write here 1 by 4 pi epsilon naught. Don't write that one, you will get confused. So what is rho here? Rho is equal to nothing but q by, this is nothing but 4 by 3 pi capital R cube I can write, and in the denominator we have already 3 epsilon naught into r is a vector here, this is into, again we have a dr. Now if you apply here, what are the constant? You take it outside. Integral dv is equal to v. So I can write this one as vd minus vs. After integration, dv is equal to v. Final limit minus initial limit, vd minus vs is equal to, you take this is as minus outside. If you want to take, you can take minus outside. So 3 get cancelled. After cancellation of this one, q is charge, that is constant, take it outside. 4 pi epsilon naught, that is nothing but 4 pi epsilon naught is also constant, take it outside. And this is r is the radius, that is also constant, take it outside. And the remaining term we left here is integral, that is nothing but r dr. Now r is what? Position. The position changing from where to where? We are calculating that one from where to where? Actually we are calculating the D point inside, right? So already you know the potential on the surface. On the surface means what is the distance of that one? That is nothing but capital R. And inside the point, what is the distance of that one? That is small r. So we are integrating this one from the surface to the point, that is small capital R to small r. Up to this you have to integrate. These are the limits of that one. So applying the limits we can able to calculate. Remaining all are constants only. So you can see this one. So if you solve this one, what is the equation we are going to get? Vd minus Vs is equal to nothing but minus q by, that is 4 pi epsilon naught r cube integral r dr is equal to nothing but, we can write as r square by 2. We can write that is lower limit is capital R, upper limit is small r. Now this one we have to solve it now. So to solve it here, I'm copying this equation here now. Now if you taken the equation of this one, there's the equation we got in the just before. So Vd minus Vs is equal to minus q by, if 4 pi epsilon naught r cube into, that is r square by 2 into small r to capital R. So in this case I can erase this one. Okay, so now what is the equation I can write? Vd is equal to, we need potential at D point, minus Vs, if you make it that side become plus Vs, so Vs minus remaining is I can write as q by 4 pi epsilon naught r cube, okay, into this is 2 also I can make it outside, that is nothing but 1 by 2 I can take it outside, and remaining is nothing but, if you apply the limits of this one, that is small r square minus capital R square. Now to solve this one, what you do is this capital R cube, take it inside, otherwise you can write this Vs formula. What is Vs? Potential on the surface. What is the potential on the surface formula? That is 1 by 4 pi epsilon naught q by radius of the sphere, that is nothing but capital R, minus this is q by 4 pi epsilon naught, that is r cube, into 1 by 2 into small r square minus capital R square. Now what you do is, if you observe this one, 1 by 4 pi epsilon naught q by r, here also 1 by 4 pi epsilon q by r, I can take it common. If you take in common, that becomes equal to q by 4 pi epsilon naught capital R if you take in common. Now this equation I can write as 1 minus, okay, this equation I can write as 1 minus. So here q is over 4 pi epsilon naught, in the place of r cube, 1 r is, okay, we taken outside, remaining is, okay, we have r square is there, 2 r square, 1 by 2 r square, that 1 by 2 r square make it inside, that means this is minus, minus into plus minus, that is capital R square by, that is 2 capital R square, it becomes small r square by 2 r square, minus into minus, that become plus. Now this is again you can take it inside, that is what is that one? Here we are already having r square by 2 r square, you can take it like this. Now here I can cancel r square I can cancel, so this equation will becomes, that is nothing but q by 4 pi epsilon naught r I can write into 1 minus r square by 2r square I can write plus 1 by 2. So if you observe this one, this is 1, this is plus 1 by 2. 1 plus 1 by 2 nothing but 3 by 2 you are going to get. So potential at D point is equal to, I can write that is nothing but q by 4 pi epsilon naught r into, that is nothing but 3 by 2 I am writing front, 3 by 2 minus, that is small r square by 2r square. Now if you observe the equation, this is the one of the potential at D point inside the sphere we got. So in this is the formula which is q by 4 pi epsilon naught r. It is similar to potential due to sphere, charge sphere on the surface. So I can replace this one with Vd is equal to, that is potential on the surface Vs. I can replace completely with Vs. Vs into what I can write, that is 3 by 2 minus small r square by 2 capital R square. This is the expression of this potential due to the non-conducting sphere inside at a distance of smaller. So this is the expression of this compared to surface. Now this is the final equation we can say. Now we can able to conclude is it correct or not. So if you want to, okay, check this, the equation is correct or wrong, just you check it. On the surface. On the surface means r value is equal to capital R. Keep the capital R, okay, that is nothing but at A point. So sorry, at B point, right? So put the R value is equal to R, what you are going to get? V. Okay, B is equal to nothing but Vs into, that is nothing but 3 by 2 minus RR. So both are get cancelled. How much you are going to get? 1 by 2. 3 by 2 minus 1 by 2. That is nothing but 2 by 2. That is nothing but 1. That is nothing but Vs you are going to get. So potential at B point nothing but on the surface already we discussed in the previous. Now center, that means if R is equal to 0, R is equal to 0 means at what point you will get? R is equal to 0 means at A point, at the center of the sphere. At the center of the sphere, if you want to calculate, so what way I can write? So R equal to 0, if you put this condition, so VB is equal to, what is the equation we are going to get? VB is equal to Vs into 3 by 2 minus R value if you put 0, this total will become 0. So that means VB is equal to nothing but, sorry, there is not B point. What this point, this is A point. Center means VA. VA is equal to nothing but how much you are going to get? That is 3 by 2 times of Vs here. That means potential at A point it becomes equal to 3 by 2 times of the potential on the surface. This is the expression already done. So this is only the point we discussed in the previous. Potential at the center is always 3 by 2 times of the potential on the surface, and as it is, okay, the point is moving from the center to the surface at any point on the surface at B point, okay, at D point, this is the potential. And on the surface, what is the potential? On the surface, the potential is already be derived. This is the potential on the surface, q by 4 pi epsilon naught, it becomes, that is Vs it becomes. So like that we can able to express the concept here. So main point is, final conclusion, potential due to non-conducting charge sphere is different at different points. At any point inside, the formula is Vs into 3 by 2 minus R square by 2R square is the formula for this. And also most important point is, potential on the surface is always, potential on the, okay, potential at the center is always is equal to 3 by 2 times potential on the surface. Means inside the potential will be more, because you have to do more work to bring the charge from infinite to the center, because the non-conducting sphere contains the charges inside also. That's why you have to do more work to bring the charge from infinite to inside the non-conducting sphere. This is the conclusion of this potential due to charge sphere concept. Now we'll discuss the graphs related to charged spheres. That graph is, we are comparing with electric field versus potential. So here we are taking the graphs for the non-conducting sphere, conducting sphere in the case of halo, and the solid. The comparison we are understanding here. And every sphere contains the center. This is the origin of the sphere. I am saying as O. This is the center of the sphere. And the line dashes line which indicates the surface of the sphere, which is a distance of R in the graphs. So here I taken the graph separately for electric field above 1, electric field versus distance graph this is, and the potential versus distance graph this is. In the case of conducting sphere, you can see conducting sphere either halo or solid, we will discuss that is. And in the case of non-conducting sphere, you can see here this is the non-conducting sphere. In the case of that, electric field versus distance graph, potential versus distance graph. Here also this is nothing but origin of the, okay, sphere, that is nothing but center of the sphere, and the dashes line indicates the distance on the surface, that is nothing but radius of the sphere, that is on the surface of the sphere line. And that means the O point is inside the sphere, R point is on the surface, and after the R point, that completely it is outside of the sphere concept. So already you know the electric field. Previously also we taken the graph of this. When you taken the conducting sphere, either halo or solid, inside the, okay, conducting sphere, electric field anywhere is 0. So from 0, that means from the center of the, from the origin to the distance of R up to here, there is no electric field exist. So that means electric field inside is equal to 0 up to this. Now after that, from the surface to outside, there exists electric field. That electric field is nothing but, you know that it is a, okay, form of a curvature. So this electric field will be like this. It will be as a looking like this. This is the way the electric field. That means in this case I can say here this electric field is inversely to square of the distance outside of that charge sphere. Now this electric field. Now what is the potential? Just before we discussed, potential never be 0 in the case of okay, either conducting sphere or non-conducting sphere. At the center there is a potential is there, and on the surface of the potential. But in the case of conducting sphere, the potential inside at a point and on the surface, that means at the origin on the surface the potential is remains same. That means potential is not 0. That's why I can say, okay, this is the way I can take the graph of this one. This is the way the graph line will be there. This is the graph where which indicates that potential is not equal to 0. So there is a potential, okay, inside, that is at a point like that is inside at center of the sphere. We can say this is on the surface potential. But if you come across a case of from the surface to outside, the potential is going to be, okay, in this case what happens, potential is going to decrease. So here I taken, okay, one of the correction will be there. What is the potential at the center and on the surface? Same means what is the meaning of this one? Potential will not be, okay, uh, it will be remain same. It will be remain same. It means this is a graph, we can say. And outside what is happens, the potential is going to be changes with respect to distance inversely to r, okay, distance of the point. So what is the potential inside? So we can write potential inside is equal to this way. I can take the graph of this one. So outside the potential is inversely to distance of that point, means potential is going to be changes with respect to distance inversely to that. And inside is anyway it is constant from center to that. That is also actually inversely to r only, but the only thing is the value of the potential on the surface and center will be remain same, and outside is going to be varies as the distances changes. So this is a graph of this one. In the case of halo or solid sphere, the graph will be remains same. Now, if you come across the case of a non-conducting sphere, this is important for us. In the case of non-conducting sphere, halo sphere graph is similar to this same thing, conducting sphere only. But in the case of non-conducting solid sphere, this is important for us. That is the part we are going to discuss here. In the case of non-conducting sphere, that is solid sphere, this is the graphs I am going to discuss for the electric field and potential with respect to distance for the case of non-conducting solid sphere case. So electric field inside at the center always 0, and you know that up to the surface, up to the radius onto the surface, electric field is directly proportional to, you know the concept, that is E is proportional to distance r. So in this case the graph line will be like this. This is the way you are going to get the graph of this. So electric field is directly proportional to distance of the point. So I can say here E is proportional to r. Now from the surface to outside, as the distance is increasing, what is happens, electric field is going to be decreases. It is similar like same, it is follows the curved path outside of this one. This is the way it is going to be. That means the electric field outside is always inversely to square of the distance of that point. So this is for the case of electric field versus distance. Now in the case of potential, what we discussed just before, potential in the case of solid sphere, that is non-conducting solid sphere, at the center it is not 0, it is equal to 3 by 2 times on the surface we said. That means this is the way I can take the graph of this one. This is at center, the potential is here, this value, and on the surface the potential is going to be decreased, because potential at the center is equal to 3 by 2 times of potential on the surface, that is ultimately equal to radius. So which is more? At the center is more. From the center to surface, what is happening? Potential is going to be decreases. The decrease in the potential curvature, we can write it as like this. This is the way the potential is going to be decreases like this. The potential decreases like this. Now from this point of, okay, from here to here, what is happens? The potential is again outside of this sphere. It is follows the inverse form of, okay, concept. So in this case I can write the potential is going to be changes as well like this outside. So if you observe the graph of this one, potential inside is, okay, this value is equal to potential at the center, and this value is equal to potential on the surface, and this value is outside. So at this point anyway outside is inversely to r, but at the center this value is equal to, how much I can say, this value is equal to 3 by 2 times of potential on the surface. So how much it is more, you can see this is the value which is more compared to the surface. Potential at C point is more than at the center. This is a graph which is referenced here. So this graphical representation comparison is most important, and you need to understand in the case of conducting halo solid sphere, non-conducting halo sphere, the graph is this one for electric field versus distance, potential versus distance graph. But in the case of non-conducting solid sphere, electric field and potential graph is this, because electric field is not 0 inside the non-conducting solid sphere, potential is also not 0 everywhere. So potential is different at different points, center will be more, tan surface, how much it is? 3 by 2 times of Vs, and here Vs this is. And at any point if you want to calculate, suppose what is the potential at this point if you want to calculate, already we derived one of the equation the previous. What is that one? Potential at D point, like we derived, that formula is equal to Vs into 3 by 2 minus small r square by 2 capital R square is the formula we derived. So this formula we have to keep in mind. This is the potential at this one of the point we can say as D point, inside anywhere from the center of the sphere to up to the radius. So this is the most important concept you have to keep in mind. Now we'll go to the next application, that is potential due to charged ring. So consider one of the ring of radius r. You can see the diagram. So here the charge is given to the ring. The ring is having circumference. So whenever the charge is given to the ring, the charges are going to be distributed linearly. That is called linear charge distribution. That is nothing but charge occupied per length of this ring. The total length of the circumference of the ring is 2 pi r. We can write. So what is the charge on the ring completely? That is q is equal to lambda into 2 pi r. So in this case, what we are doing is we taken one of the axis from the center of the ring, and at a point of distance, this is at p point you can say. Now what is the potential due to this charged ring at that point we are going to calculate. The point P which you chosen that point is at a distance of x from the center of the ring. So that x value equal to 0 if it is at the center, and from the center it is going to change now. So here to calculate this one, this is the linearly charged distributed ring. So that's why I'm taking a small elementary portion here, ring, and on this the charge of this one is equal to dq. If you say, now the charge dq is equal to, in terms of linear charge density, we can write as lambda into q is equal to lambda into 2 pi r complete. Now dq is equal to lambda into, we can write as nothing but the small elementary portion which is there, how much angle it is making, that is you can write as dr. We can write elementary length of this, otherwise dl we can write. Don't take dr, that is you can take it as dl, elementary length of that. So dq is equal to lambda into dl, this length of this portion which you chosen is equal to dl you take. Now we need to calculate the potential at this point. So potential at this point means from the elementary charge to the point, you take a line joining of this one. This is the distance of the point from the charge which is taken. The distance of the point from the charge I can take it as A. So I can write potential at P point is equal to, according to basic expression, 1 by 4 pi epsilon naught into charge. What is the charge here? That is elementary charge dq by distance of that one. What is the distance? That is A. This is the expression for potential at that point P. 1 by 4 pi epsilon naught dq by A. Now what is dq? dq is nothing but lambda into dl. We can apply here. That is nothing but dp is equal to 1 by 4 pi epsilon naught into, that is lambda into dl by A. For the small elementary portion, the potential is also small, that is dvp we can write. Now you can integrate this one both sides. Integral dvp is equal to potential vp I can write. Now 1 by 4 pi epsilon naught is constant, no integration, that is 4 pi epsilon naught you take it, lambda by A. Okay, in this case A is also, if you want to take it you can take it outside, but okay, the distance of the point is same. Now this is integral dl. Now integral dl means length value changes, because I can change the length of this small portion from dl to up to what size I can take, up to the complete circumference of the ring I can take. That means this you have to take it as 0 to 2 pi r. Up to that you are going to. Now if you solve this one, vp is equal to, simply I can write 1 by 4 pi epsilon naught into, that is lambda by, okay, what is a value? A value is equal to, from this diagram if you see this, we are getting a one right angle triangle here. So in this case if you apply the Pythagoras theorem, it becomes, a value becomes under root of r square plus x square here. So if you apply this value you are going to get a value is equal to, that is r square plus x square you are going to get into integral dl is equal to length, you will get that length is 0 to 2 pi r. If you apply the limits, that value you are going to get 2 pi r directly. Integral dl is equal to L is equal to, lower limit is 0, upper limit is 2 pi r. If you apply this is the expression you are going to get. And if you want to cancel here, 2 pi, 2 times it will get cancelled. So I can write the expression here as potential at P point is equal to what I can write, that is lambda r by, this is lambda, this is r by, that is 2 epsilon naught into under root of r square plus x square is the formula. Now we will conclude that potential due to charged ring using the graph. You can see the graph here we taken already. First, before that, we have to understand the equation already which we derived in the previous. Potential due to that charged ring at any distance of x equal to lambda r by 2 epsilon naught under root of r square plus x square we got. What is lambda? Charge per length, that is q by 2 pi r. So if you apply that, after that rearranging, we got q by 4 pi epsilon naught r under root of r square plus x square. You will get r get I cancel. Finally, you get this equation v is equal to q by 4 pi epsilon naught under root of r square plus x square. Now put the x value is equal to 0. X value 0 means at center of the ring. At the center of the ring, what is the potential value? X value 0 if you put it. So v value is inversely to r here, because q by 4 pi epsilon naught is anyway constant, root r square value, r square and root get cancelled, you will get v is inversely to r. So there is a potential v there. Now this is a one concept. If x equal to r, if you say, that means if the distance of the point equal to radius of the circle, if you taken x equal to r, then v is inversely to r square plus r square becomes, okay, that is 2r square. 2r square means that is r square, if you take it outside, that is inversely to root 2r here. So that means this denominator value is going to be increases. That means automatically potential is going to be decreases. So potential at the center is less. Potential at the center will be more because this value is according to that one. So in this case, what is happens? Potential will be changes as the distance is changing. That means at the center, the potential value will be maximum. Okay, more. As the distance is increasing, potential value is going to be decreases. Distance is increasing, potential value is going to be decreases. So in this case, potential is going to be decreases up to infinite, and potential is going to be decreases up to infinite both the sides. This is the concept of this graph we need to understand here.